All right, hi everyone. Thank you for being here at this talk. And I know the title might seem like a bit of an oxymoron, iceberg and real time, but hopefully by the end of this, you'll understand exactly what we mean and hopefully take away some of the tricks and techniques that we learned to get you that lower latency and data freshness that you all look for. A little bit of introduction. I'm the senior product manager at VeloDB, but the true brain behind all of this is actually my partner, Owen. He's going to be able to help take a lot of questions, and a lot of this content is developed by him, so I want to make sure that he gets a nod before we move on. So here's a brief agenda of what we're going to go through today. So first, wanted to kind of touch on what do we really mean by real time here, and why do we think it's a really important application in today's day and age with all of the technology advancements, especially AI. I'm going to talk about some of the challenges. Most of these are probably familiar with a lot of you, but we just want to make sure that we align on that. And then I want to talk about some of the key technologies that is going to be able to bring that real time, that data freshness, that low latency and concurrency that we all wish for. And then as well as extending beyond kind of Iceberg and Lakehouse, what are some of the other things that we're able to handle? And a bit of roadmap in terms of what we're working on with icebergs between Apache Doris, VeloDB, and then of course some of the details around the community and then commercial support. So if we look at some of the uses of real time, some things that may come into mind, such as on-demand customization, on-demand analytics, very popular in the gaming industry. And traditionally, we call these things such as operational analytics, right? You need to be able to take in that fresh data quickly. But then it started to evolve, right? We started getting agents, right? There's a lot of conversation that's happening, and you don't really want to wait 30 seconds to be able to do something, to be able to respond to something. So that demand to have a more lifelike latency is emerging. And then at the same time, because of agents, AIOps is getting a new coat of paint, right? Incident management, the real-time remediation is now coming back again. So in the IT world, the need for real-time has also grown due to these agents. So because of all these three reasons, the traditional, the AI, and what it causes, real-time becomes a lot more important. Now, quickly recap, what are some of the challenges? Well, first thing is, we need to, when we're talking about lakehouses, right? There's a huge challenges with the IOs. S3 is generally bounded by, what you can actually kind of push data in and out. So that's a big challenge. Also, that also affects your concurrency because again, more concurrencies, more network traffics, you have that same problems. And again, related to that problem is also the ability to scan data efficiently. You don't really want to scan more than you need to because every scan you take, every time you go and fetch something, that's network travel, that's going to affect things, right? So kind of summarizing, really need to make sure that I/O performance is taken care of. We have efficient planning, scheduling, and scanning. And then we also want to be able to read files, relatively quickly so that we can actually get to that data. And this is all on the read side because in a lakehouse, in a share everything world with Iceberg, a lot of the write are done separately through streams, through batch, etc. So for the part with Iceberg, we're going to particularly focus on the read side. And then we're going to talk about what we do on the write side as well, which gets really interesting too. A really quick introduction. So one of the key technology that powers these sets of use cases is called Apache Doris, which is a MPP engine with a storage engine as well. So we call this a real-time hybrid database because we're able to bring these real-time capabilities to different use cases. It's hybrid because not only it can do traditional SQL, it can also do hybrid searches and full document searches. And then finally, it's a database because we have not only a query engine, but also a storage engine as well. So really kind of, bringing that together. It's a relatively big community. We have over 700 contributors, 14,000 stars on GitHub, and 5,000 plus users, and it's growing. Started out in the APAC region, and now it is gaining more traction globally as well. I don't think I need to talk about too much about this, right? This is just for reference. We all know about Iceberg. That's why we're here today. Modern table formats, a lot of quality of life stuff, fixes a lot of the problems around interoperability, and great benefits, and many versions in the future. So now I'm coming to the meat of the conversation, right? Bring these analytics onto Lakehouse with Iceberg. So brief recap before we get into how we do some of these things. This is just an overview of where Apache Doris sits in that lakehouse stack. So if you kind of go from the bottom, you have your raw storages, you have your open table file formats, and then you have your table formats, and then Apache Doris is on top. So it's a collection of capabilities that brings together this high-performance querying on lakehouse. So we have data cache layers, and in fact, there's actually many layers of caching, and we'll get into details about that later in our conversation. There's also a variety of different process layers. So for example, we have a vectorized engine. There's a lot of performance enhancements, materialized views, cost-based optimizers, and so forth. We'll dig into some of these details as well. And on the access layer, this is very much compatible with the MySQL protocol. It is ANSI SQL, but anyone who's familiar with MySQL is going to find it very easy to use Doris. And of course, we have open storage APIs as well. And the best part about this architecture is that we can query multiple catalogs. So whatever catalogs you choose to use, you can query all of them. They can manage all your tables. So whether that's Unity, Polaris, Gravitino, which is a new one that's coming up, or even just traditional old HMS. Doesn't really matter. You can query across all of these. And we do a lot of predicate pushdowns and federations down to share, to basically have some efficiencies. And of course, this feeds into all the use cases that I mentioned earlier. So what are some of the tricks, right? So first we talk about I/O optimization. So here we do a couple of things that's really interesting. So the first thing is that we prefetch. So instead of waiting to actually for data to be fetched, we can read ahead and prefetch a lot of these data before we need, so we can minimize the I/O wait time, about 60 to 80%. And then speaking of caching, you saw that data cache there, we actually have multiple caches. So we can distribute it, that metadata cache, across. So we're minimizing the amount of times that we're actually going to fetch the metadata itself from the Iceberg metadata in S3. We're trying to get that locally as much as possible. Again, minimizing that I/O. So altogether, we're able to really save up to 95% in terms of reducing that data scan volumes just by doing these things. So minimizing that latency by reducing network travels as one of the big limitations. Second thing, this is where some of the intelligence really comes into play, right? We talked about well, you do a lot of scan, right? But you really need to do all of these things. If we can intelligently prioritize based on data localities, really think about complexities ahead of time, and we can minimize and prioritize the scans in an intelligent order to minimize that latency. And then on top of that, instead of unnecessarily scanning partitions during runtime, we can think about do we really need to actually go to all these partitions as we're thinking through all of this? And this again allows us to really create a situation where we can deliver predictable latencies, as well as reducing latencies by 70 to 90%, compared against just a traditional standard Iceberg scan. Again, adding to that latency reduction. And then we talked about file read. So this is where we're starting to get to some of the core capabilities of Doris, not just on Icebergs as well. So we have a native Parquet reader. So we purpose-built this to be able to bypass a lot of the generic interfaces so we can really get to that file quickly and process it. We do predicate pushdown, so this is for all of the lake access, as well as linking into some of the data access, so we can really push all the filterings into the storage layer, minimizing the amount of data that actually gets shuffled back and forth. And we also do something called the lazy materialization, and materialization is actually a big part of how we bring a lot of that real-time capabilities and latency reductions into a lakehouse. And here is that we're actually deferring column loadings into that until it's actually needed, so that we're not loading all of these, we're not materializing all of this data until it's actually needed. Again, minimizing I/O. So again, all of this is really additive in terms of how we actually deliver on that performance optimizations while we're reading on lakehouses. So I mentioned materialized views, and we really see that as the bridge between a lake and a database. Because if you really look at the two, right, what is the difference, right? For a database, there's a lot of storage optimizations and materializations that happens. And that's really necessary to get to that last mile, because you can try to be smart and take all the trade-offs, but you just can't beat physics sometimes, right? So we don't try to hack physics. Instead, we just go along with it. So we actually have materialized storage. So this is pretty standard. We compute the aggregates, the joints, and you can basically transparently materialize that. We also automatically do query rewrites. So you don't actually have to worry about where you're actually pointing your queries to the files or storages. We do that automatically. So as long as you create your view, any changes, we basically handle a lot of that. And we also do partition level refresh. So when the data refreshes, instead of building that entire materialized view, when the source data changes, right, we actually can intelligently only refresh the partition that is affected. So therefore, you're reducing the overhead. So you can actually have your materialized views kept up to date without having to incur that additional resource consumption. And just to kind of give you an idea of what this showcase looks like, this is about 42 times speed up. So really, really orders of magnitude faster, millisecond response times. And of course, we can increase the concurrency by 5x. That's how much we can actually do with these materialized views. And you can see on the diagram to the left, the materialized views and the caching layers that we have in terms of how we actually point our queries to in terms of getting the data and the various layers that it can go from. So that's a bit about Iceberg. But there's more. All of these things are performance optimizations that are inherent to Doris, and they're all additive. So I talked about a lot of these, and the addition of all of these things get us the performances that we show you. So it's not just one silver bullet. It usually never is, right? It's the number of these things that are added up together, and that's how we achieve a lot of these gains. But what about beyond Lakehouse, right? What is it? So we really want to talk about what else can you do with Doris aside from querying Iceberg on Lakehouse. You know, it's interoperable, it's great, but oftentimes you have things that require you to do a bit more SLA. Maybe, you know, streaming or writing to Lakehouse and then reading it, it's still too slow. Even though there's some really nice advances, in the recent times, sometimes you really need that extra layer where we actually offer a storage couple mode so that we can actually write into our own format if necessary. Again, if necessary. And there we have some really good capabilities around streaming ingestions and data consistencies, because we want to make sure that your data remains consistent as it's landed through the streams. So we integrate with native Kafka's, Flink, as well as able to really maintain data consistency through a set of techniques. And we do this at a multi-table level, not just a single table level. So we have transaction isolations to make sure there's ACID compliance across all the partitions. We actually have a two-phase commit so that we can make sure that we have that consistency guarantee. And between the streaming side and the Doris side, we maintain exactly once semantics to prevent duplicate ingestion so that you're not getting messy data as it comes through. And then, of course, we're handling a coherent schema and Materialized. So really able to enable this real-time streaming data as well as providing that consistency, whether that's landing in Lakehouse directly or in the Doris owned storage. So that's the first thing. Second thing is, we talked a lot about reads, but we don't really talk a lot about updates, right? Writing is where a lot of fun things and problems happen, right? With Lakehouse writes, it's traditionally append only. You typically have to make trade-offs between paying the taxes up front, in which case your write's going to be a bit slow because you're merging the files as you're writing, or you pay the taxes on read, which you have to merge the files when you're reading. But we can actually get the best of both worlds. We actually can do not only append-only updates, but actually insert updates and delete operations as well. And this can be done in both. This is done in that proprietary storage that we have. But even when writing Iceberg files, there's also techniques that we can actually add to accelerate the trade-offs between read and write. So when we're writing these micropartitions, we can also write a set of metadata on top in our own storage. So we create a bitmap or indexes to those partitions. So when you're actually at the time of reading, instead of doing merge on read for the files, you can merge the indexes and the metadata. so that you don't have to pay as much tax when you're reading that data. And this is purely because we're able to write that index as we're writing the Iceberg files. And of course, when it comes to non-icebergs, we actually support partial updates as well. So that, again, accelerates the ability to make sure that we maintain that read speed as we're updating, so that we can have fast reads as well as fast writes. So the diagram on the right shows what happens when we actually write with this additional techniques. We call it merge on write versus just a traditional merge on read. So you can see like multitude of 4x improvements. And if you actually add page caching along with that, it goes down even further. You now are also able to benefit all of the caching performance gains as well. So that includes materialized views. Just going to recap. I'm not going to talk too much about this. So this is some of the out-of-the-box benchmarks that we ran against some of the other engines. And the highlight is average data latency, 1 second. Average query latency, 100 milliseconds. And 10,000 plus QPS. This is what we're able to deliver based on all of the performance techniques that we've added, as well as the inherent nature of Doris being an MPP engine, highly vectorized, and so forth. I mean, many people probably say this, right? I probably can't get away without talking about AI. So we're going to talk about this a little bit because you have to kind of. So I said earlier that Doris isn't just limited to lakehouses or a database. For the past 3 years, us at VeloDB, we actually invested a lot into document searches, hybrid searches, and full text search and structured searches. So because we understand that trying to use vectorized capable general purpose databases is often more efficient than trying to get a fit for purpose vector source, because then you run into the polyglot persistence problems of having way too many data stores and engines and things to manage, and operation and architecture complexity gets out of hands. There are techniques to do that, but again, really hard to beat physics. Much easier when everything is stored together. And in our case, it's very easy to perform these hybrid searches where you can just use your select statements, and it's the where statements where a lot of these magic happens. And again, just a couple of reasons why you might want to put these together. Again, hybrid search capabilities, being able to search structured data with your text informations, as well as the ability to handle large volumes. So really being able to kind of take on multiple sets of workloads with one engine, unifying all of these and simplifying your architecture. So a little bit about what we're doing with Iceberg, because again, we're here at Iceberg Meetup. We want to look at our Iceberg roadmaps. So just a quick summary of what we can do today. So we already have the ability to both read and write operations. We have full catalog integration, so no matter who is managing that Iceberg table, not a problem. Of course, time travel and branching and tagging support. So your basic sets of all the V2 stuff is mostly here. But what's really exciting is coming next and next beyond. Because we know that V3 has already dropped, so we're already in works with V3. Variant will get very interesting in the near future, especially with some of the hybrid search and AI capabilities. We're also in process of working on these fully managed Iceberg tables, so we can, again, take that acceleration a bit further by managing that with Doris. And one of the things that, again, will accelerate performance even further real time is that incremental materialized view updates. So again, we're taking this even a step further with Iceberg, so that when you're creating these materialized views on top of Iceberg, it will also benefit from that partial updates as well. Last but not least, I wanted to spend a little bit of time talking about the community and commercial support. So here are some informations about the Doris community. So I'm going to pause if anyone want to take a picture and reference. So we have, GitHub, we have Slack, we have a set of documentations, and also you can find us on LinkedIn, YouTube, Mediums, and all sorts. And this is an open source community. Welcome everyone to kind of join and check it out. This is where you can find a lot of relevant informations and trainings. And finally, I want to talk a little bit about VeloDB So we're the company that is commercializing Doris. In fact, the founding member and a lot of the contributors and the PMC chair are from MelloDB, and we're constantly giving back to the community. In fact, we're probably giving back most of the actual code bases. The only thing that we really keep for ourselves are a lot around the security, enterprise features, really trying to make sure that we give you the best out-of-the-box experience possible so that you can really get started building what you care about. Right? Really bridging that open source innovations and enterprise readiness. We offer a fully managed cloud offering, and we also, of course, offer BYOC and a lot of the enterprise software as well, fully compatible with K8s or VMs. That's all I have today. I purposely left some time for questions, so happy to take any questions, and Owen and myself can help to address any that comes by.
Use the mic. We're going to use the mic for the questions.
Yes. Yes?
Wait.
Daniel.
Sorry, it doesn't get picked up by the camera otherwise.
So trying to understand most of the optimizations that you describe on top of the Iceberg tables, they must be sitting on top of the internal storage of Doris for all of these gains to be realized? Because traditionally, most of the Iceberg tables are sitting, on an object store, the data sitting there,
Yes.
and then the metadata is sitting on a catalog, and that part was not there. Like, I understand all the optimizations you did to speed up reads, but it was not clear because, like, for example, predicate pushdown cannot happen into object store, right? So how is that is actually laid out?
Owen, you want to take that one?
Can you repeat the question?
So the question is, how do we do predicate pushdowns into object storage?
Okay, that's a good question. Yeah, we have implemented a native file reader for Iceberg. Yeah, so we can control how can read the data from the file. So if we have a predicate, we can calculate which column we should read, and then we just read the columns, the rows from the object storage.
Cool. Yes, sir.
Is there a performance difference between running on the native storage versus the Iceberg storage?
Yes. Yes. We can, I think, offer additional 3x accelerations when you're running this in a native storage, the storage that we have versus Iceberg, yes. You want more to add? Okay.
Yeah, okay, there we go.
Thank you.
Thank you. Yeah.
Yeah.
It's much faster for the native engine because that we have rich index, for example, the primary index, inverted index, and vector index, Bloom filter index. We write many index to optimize for the data lookup. So it's much more faster and it can support much more concurrency. Yeah. So if you want, if you need second or sub-second level real-time queries, you can try the native query engine. Yeah. And we have a solution that we call better together. If you need the second or sub-second level real-time latency, you can ingest your data into MelloDB native storage engine, and then MelloDB can write back the data to the lakehouse such as Iceberg, and it can be shared to other query engines. Yes, so you can use the better together solution to get both real-time latency and open access.
Yeah, on that part of the storage layer, internally it sounds like it'd be 3 times more efficient, but this is a question, I don't know how Doris does its data resiliency model, because object storage will take care of protecting the data, but how does Doris takes care of like the data not actually being lost? Like, is that, when it's run in a distributed mode, does it make copies of the data internally? How does that work?
So you mean the durable of the data inside the MelloDB or Doris? Yes, Doris is a distributed database, so it handles the distribution of storage and durable by replicas. Yeah, so it handles the distributed details by itself. Yeah. And then the Doris was created by us 12 years ago, and it has been used by more than 5,000 companies all over the world. So it's very stable and ready.
So for the materialized views, I think it's not in the standard, but I think it's coming in the version 3. So how the metadata catalog supported and how do you support it? So is it in the standard materialized views or is your own materialized view?
Yes, currently it's our own materialized view. Yeah, users can define the materialized view in Doris and ValueDB, and it will read data, run the queries, and write the data to the materialized table inside the ValueDB. Yeah.
So then is it in your own data format, file format, or is it still the Iceberg format?
Yes, it's in our own format, but it can also be run back to Iceberg to be read by other query engines in the Iceberg format.
Okay, thank you.
Any other questions? All right, thank you guys so much for being here and speaking.
Thank you.
Thank you, everyone.